Black holes swallow everything: light, matter, information, and yet without them, stars would burn too fast, galaxies would collapse too soon, and Earth would never have existed. Today we find out why the most destructive objects in the universe are also the reason we're here. Let's begin now. Right now, as you listen, this something is out there. Not far in the way a distant city is far. Not far in the way another continent feels far. 26,000 light-years away, buried at the heart of the Milky Way, something sits in perfect, absolute darkness. It weighs as much as 4 million suns pressed into a single point. It produces no light, no heat, no signal of any kind that human eyes could ever detect. And yet, every single star in our galaxy, including the one that keeps you alive, is circling it. Let that settle for a moment. The entire galaxy you were born into, the one that contains every planet, every star, every nebula you have ever seen in a photograph, is orbiting something invisible, something that has never once announced its presence with light, something that simply sits there, bending the fabric of space around it with a gravitational grip so complete that even the concept of escape becomes meaningless. And here is the part that should genuinely unsettle you. This is not unusual. Look out across the observable universe at the hundreds of billions of galaxies spinning through the dark, and you will find the same arrangement repeated almost without exception. Every large galaxy, nearly every one we have ever studied, has one of these things anchored at its center, controlling everything around it, seen by nothing. So the question worth asking is not how they form, not what they look like up close. The question is something more fundamental, something that cuts deeper into the nature of reality itself. Why does the universe insist on making them? To answer that, it helps to be clear about what a black hole actually is, because the name does it a disservice. A black hole is not a hole. It is not empty space. It is not a void or a gap or a tear in the cosmos. It is matter. Real, physical matter that has been compressed past every defense the universe normally provides, against infinite collapse, past the resistance of atoms, past the pressure of subatomic particles, past every force that ordinarily keeps things from falling in on themselves, until the geometry of space and time itself curves so sharply inward that nothing, not even light traveling at 300,000 kilometers per second, can climb back out. That is a black hole, not an absence. A presence so extreme it rewrites the local rules of reality, and they are not rare. Astronomers estimate that tens of millions of black holes are drifting through the Milky Way at this very moment, the collapsed remnants of stars that burned out long before our sun was born. Most of them are invisible. Most of them will never be directly detected. They move through interstellar space in silence, warping the paths of anything that strays too close, leaving no trace except a slight gravitational nudge on the surrounding darkness. We cannot see them. We cannot touch them. We cannot send a signal into one and expect anything back. The moment something crosses the boundary of a black hole, it is gone from our universe, in every meaningful physical sense, causally disconnected, unable to influence anything on the outside ever again. And yet we know they are there, not because of faith or assumption, but because the universe itself does not work without them. The galaxies do not hold together the way they do without them. The stars do not form at the rates they do without them. The very structure of what we see when we look up at the sky carries their fingerprints everywhere. We know they exist because the universe cannot function if they don't. That is not a small statement. That is the entire puzzle. If the thing controlling our entire galaxy is completely invisible, what else might be influencing us right now that we haven't discovered yet? But to understand why these things exist at all, we have to start somewhere smaller. We have to start with a star that is dying. Because the way a star dies, the specific, brutal, almost absurdly violent physics of stellar death is where black holes come from. And once you understand that process, the night sky will never look quite the same again. Here is something that textbooks rarely frame correctly. The sun is not burning, not in the way a campfire burns, not in any ordinary chemical sense. What the sun is actually doing at every moment of every day is exploding and collapsing, At the same time, two catastrophic processes running simultaneously, each one powerful enough to destroy the entire structure on its own, each one precisely cancelling the other out. Remove the nuclear fusion happening in the Sun's core right now, and the whole thing, all 700,000 kilometers of it, collapses inward under its own gravity in roughly 30 minutes. The same mass that took billions of years to form would crush itself down to a fraction of its current size in half an hour. Remove gravity, on the other hand, and the fusion energy pouring out of that core has nothing to push against. The Sun would simply blow itself apart over the course of a few hours, plasma scattering across the inner solar system, every atom dispersed into space. What keeps those two forces from winning is the fact that they are perfectly balanced against each other. And that balance, that delicate knife-edge equilibrium between explosion and implosion, is the only reason Earth exists, the only reason liquid water exists on its surface, the only reason anything alive has ever drawn a breath. Life on this planet depends entirely on two forces of annihilation, agreeing to cancel each other out, for now, because that balance is not permanent, it is a countdown. For a star the size of the Sun, the countdown is long, roughly 10 billion years from start to finish, and we are about halfway through. But for a star that is 20, 30, or 100 times more massive, the clock runs incomparably faster. The physics are different. A more massive star needs to generate far more outward pressure to support its own weight, which means its core has to run hotter, which means nuclear reactions proceed at a furious pace, burning through fuel at a rate that makes the Sun look leisurely by comparison. A star 100 times more massive than the Sun might exhaust its core hydrogen in just a few million years, a cosmic eye blink compared to the Sun's 10 billion-year main sequence lifetime. And when that hydrogen runs out, the star does not simply stop. It begins a desperate sequence of escalations. The core contracts. Temperature rises. When it gets hot enough to fuse helium, helium fusion ignites, buying the star more time. But the helium phase lasts only a fraction as long as the hydrogen phase. Then the helium runs out, the core contracts again, and carbon fusion begins. Then neon, then oxygen, then silicon. Each stage burns hotter and faster than the last. Each reprieve is shorter than the one before. The star is accelerating towards something it cannot avoid, burning through millions of years of stability in centuries, then decades, then days. Silicon fusion, the final stage, lasts only a matter of days. After millions of years of steady hydrogen burning, a massive star can exhaust its last viable fuel in less time than it takes a season to change. And at the end of that silicon burning, something accumulates at the center of the star that changes everything: iron. Iron is not just another element in the sequence. It is a trap, and the universe built it right into the structure of nuclear physics, with no exits. Every fusion reaction before iron works the same way. Combine lighter nuclei, release energy. Use that energy to push outward against gravity. Hydrogen into helium releases energy. Helium into carbon releases energy. Carbon into neon, neon into oxygen, oxygen into silicon, all of it releases energy. That energy is what keeps the star alive, what keeps the outward pressure going, what keeps the whole structure from collapsing. But iron sits at the absolute peak of what physicists call the nuclear binding energy curve. It is the most tightly bound nucleus in nature. Fusing iron into anything heavier does not release energy, it consumes it. You have to put energy in to make heavier elements from iron. The nuclear furnace cannot burn iron. There is nothing left to burn. The moment the iron core reaches a critical mass, roughly 1.5 times the mass of the Sun, the outward pressure vanishes almost instantaneously. Not gradually, not over centuries. In a fraction of a second, the support structure that held the star up for millions of years simply ceases to exist. And gravity, which has been waiting patiently since the moment the star first formed, finally wins. What happens next is almost impossible to picture at human scales. A core, roughly the size of Earth, containing more mass than the Sun, collapses inward and reaches a diameter of about 20 kilometers in less than 1 second. The density climbs to values that have no everyday equivalent. A single teaspoon of that collapsing material would weigh more than the entire Himalayan mountain range. Electrons are crushed into protons. Protons become neutrons. A flood of ghostly neutrinos bursts outward through the collapsing material. The temperature spikes to hundreds of billions of degrees. All of this happens in less time than a single heartbeat. A star spends millions of years carefully, steadily burning through its fuel, then burns through everything that remains in a matter of days. Honestly, that is the financial behavior of every final year university student who has ever existed. If iron is the star's death trap, why did the universe design nuclear fusion to stop exactly at iron and not at some other element? That collapse happens in under 1 second. But what occurs inside that 1 second created every heavy element on Earth and raised a question that physics spent 50 years refusing to fully face. When a massive star dies the dramatic way the universe makes sure everyone knows about it. The shockwave born from a collapsing core tears outward through the star's outer layers at 30,000 kilometers per second, roughly 10% of the speed of light. Everything in its path gets blasted into space. Hydrogen, helium, carbon, oxygen, all the elements the star spent millions of years building up, flung outward in an expanding shell of superheated plasma. And for a few weeks after that, something extraordinary happens. The dying star, in its final act, in the last gasp of its existence, outshines its entire host galaxy. Not just the stars nearby, the entire galaxy. Billions of other suns combined are dimmer than this single stellar death. These events are called supernovae, and they are among the most violent things the universe produces. But there's something even more remarkable buried inside that violence. The extreme temperatures and pressures generated during a supernova are so intense that they force atomic nuclei to fuse in ways that are impossible under normal stellar conditions. Elements heavier than iron, which the star's own fusion couldn't produce, are forged in these final moments and scattered across space. Gold, platinum, uranium, iodine, silver. Every element heavier than iron that exists anywhere in the observable universe was created in events like this, or in the collision of neutron stars, and then distributed through space by the explosion itself. The gold in any ring you're wearing was forged inside a dying star. The iodine your thyroid depends on to function was scattered across space by a stellar explosion billions of years ago, eventually incorporated into the gas cloud that became our solar system, then into the rocks of early Earth, then into the precessed ocean, then into you. You are in a very literal and chemically precise sense made of dead stars. That is an astonishing death, a death worth noticing, but it isn't the most terrifying kind. In 2009, astronomers monitoring a galaxy called NGC 6946, about 22 million light-years away, were watching a massive star. It had been brightening slightly the way massive stars sometimes do in the late stages of their lives, suggesting that something significant might be coming. And then over a period of a few weeks, it simply got dimmer and dimmer. And then it was gone. No supernova. No burst of light visible across the galaxy. No expanding shell of gas. No neutron star left behind as a remnant. When the Hubble Space Telescope was pointed at the exact same patch of sky, there was nothing there. Just the quiet background of distant stars and empty space where a star 25 times the mass of the Sun had existed moments before on cosmic timescales. This star, catalogued as N6946, BH1, had almost certainly collapsed directly into a black hole without a supernova at all. Here is what most likely happened. The star was so massive that when its iron core collapsed and the shockwave began pushing outward, it didn't have enough energy to fight through the enormous weight of the outer layers pressing down on it. Those outer layers, tens of solar masses of hydrogen and helium, simply fell inward. There was no explosion powerful enough to overcome them. The shockwave stalled and died inside the star, and all that material joined the collapse, adding its mass to the growing black hole. From the outside, A star that had been shining for millions of years, brighter than the sun by tens of thousands of times, simply dimmed and vanished. No announcement, no fireworks, no evidence that anything had happened at all, except that something which had existed was no longer there. This is called direct collapse, and it is in many ways the more unsettling path to a black hole. A supernova, at least, tells you something happened. It leaves behind a remnant, a shockwave, a cloud of expanding debris you can study for thousands of years afterward. Direct collapse leaves nothing, not even a tombstone. And current evidence suggests this pathway may be more common than we once thought, particularly for the most massive stars, the ones whose outer layers are simply too heavy for any shockwave to escape. Two very different deaths, one dramatic and visible across half the universe, one quiet and completely invisible, announcing itself only through an absence, and both lead to the same place, a region of space-time so severely curved that light itself cannot escape. Before we go further, a quick note on what happens when the collapse doesn't quite go all the way. Not every massive star collapses into a black hole. For stars in a certain mass range, the collapse stops at an intermediate state, a neutron star. These objects are genuinely extraordinary, about 20 kilometers across, more massive than the Sun, spinning hundreds of times per second, with magnetic fields 1 trillion times stronger than Earth's. A neutron star is so dense that a single teaspoon of its material would weigh as much as a mountain. What holds a neutron star up against gravity is a quantum mechanical effect called neutron degeneracy pressure, a resistance that arises because neutrons, like electrons, obey the Pauli exclusion principle, which prevents two identical fermions from occupying the same quantum state. In a neutron star, this effect is all that stands between the object and further collapse, but it has a hard limit. Above roughly 2 to 3 times the mass of the Sun, the exact threshold, depending on the still uncertain equation of state of nuclear matter, neutron degeneracy pressure is overwhelmed. There is no known force in the universe that can provide additional resistance. No exotic particle, no undiscovered interaction, nothing in the standard model or beyond it that we currently understand can stop what happens next. The collapse continues. Space-time curves past the point of no return. And this is the detail that matters most. This isn't a failure of physics. Nothing has gone wrong. The universe isn't making an exception. What's happening is precisely what the laws of physics predict applied without compromise to an extreme condition. When mass concentrates beyond a certain threshold, the geometry of space-time doesn't just bend, it closes. And nothing, not neutron pressure, not any other force we know, is exempt from that consequence. The universe doesn't negotiate. If both kinds of death, a spectacular explosion and a silent disappearance, can create black holes, what does that tell us about just how unavoidable black holes are in this universe? But both of these pathways produce black holes of at most a few dozen solar masses. Something weighing billions of times the mass of the Sun is sitting at the center of nearly every large galaxy, and where those came from is an entirely different mystery. One that begins with a man dying in a World War I trench. December 1915. The Western Front is frozen. The Eastern Front is worse. Karl Schwarzschild is serving in the German artillery on the Russian front. He is 42 years old. He has contracted a rare autoimmune disease called pemphigus, his immune system attacking his own skin, causing it to blister and peel. He is in constant pain. His condition will kill him within 6 months. By day, he calculates artillery shell trajectories for the German army. By night, by the light of a candle in his tent, he is doing something else entirely. He is working through the mathematical implications of a paper that Albert Einstein had just published, the general theory of relativity, which had arrived at the front somehow in the middle of a world war. Einstein's theory describes gravity not as a force pulling between objects across empty space, but as something more fundamental and stranger, the curvature of space-time itself, caused by the presence of mass and energy. Massive objects don't pull on each other. They curve the fabric of space-time, and other objects follow the curved paths that result. What we experience as gravitational attraction is actually the geometry of space and time guiding matter along the straightest possible paths through a warped landscape. Einstein had encoded this idea into 10 coupled nonlinear partial differential equations, his field equations relating the curvature of space-time to the distribution of mass and energy within it. Elegant when written in the compressed language of tensor calculus, ferociously difficult to solve in practice. Einstein himself had not found an exact solution. He didn't expect one to exist in closed form. The equations were simply too complex. Schwarzschild found one anyway. Working through the nights in pain on a battlefield, he derived the exact mathematical description of space-time around a perfectly spherical, non-rotating, uncharged mass. He sent his solution to Einstein in December 1915, just weeks after the theory was published. Einstein was genuinely astonished. He presented Schwarzschild's work to the Prussian Academy of Sciences in January 1916. Schwarzschild died in May 1916. He never learned what his solution would eventually reveal about the universe. He was 42 years old. What Schwarzschild found embedded inside his solution was a parameter that would later be understood as one of the most consequential numbers in all of physics. For any spherical mass, there exists a critical radius, now called the Schwarzschild radius, such that if the entire mass of the object were compressed inside that radius, something fundamental changes about the space-time geometry surrounding it. The mathematical terms describing how time passes and how distances are measured change their character completely at that boundary. The numbers are striking in their specificity. For the Sun, the Schwarzschild radius is about 3 kilometers. The actual Sun is roughly 696,000 kilometers in radius, safely enormous compared to its critical threshold. For Earth, the Schwarzschild radius is 9 millimeters, approximately the size of a marble. For a human body of 70 kilograms, it is smaller than an atomic nucleus by a factor of 100 billion. Here is what these numbers actually mean. They are not exotic curiosities that apply only to strange objects in the distant universe. Every object with mass has a Schwarzschild radius. The universe, in a sense, always keeps track of it for every rock, every planet, every star, every galaxy. The physics never stops calculating whether the threshold has been crossed. The only question is whether the compression is achievable. For ordinary matter, it isn't. The electromagnetic forces holding atoms apart, the quantum pressures preventing electrons and neutrons from occupying the same space. These forces keep ordinary matter at densities far above its Schwarzschild radius. A human body would need to be compressed to the size of 100 billionth of an atomic nucleus to become a black hole. That doesn't happen. But for a stellar core that has lost its last source of outward pressure, it does. For decades, after Schwarzschild published his solution, most physicists treated the critical radius as a mathematical curiosity, a strange feature of the equations that probably had no physical relevance. Einstein himself argued that nature would never actually produce objects compressed to their Schwarzschild radius. Surely something would intervene. Surely the equations were breaking down, not describing reality. It wasn't until the 1960s, nearly 50 years after Schwarzschild's work, that physicists fully understood what that boundary actually represents. The event horizon is not a wall. It is not a physical membrane. There is nothing materially special about the location in space where it sits. A person falling into a sufficiently large black hole would feel nothing unusual at the precise moment of crossing no barrier, no jolt, no physical signal of any kind. The tidal forces that would eventually tear them apart are still manageable at the event horizon of a massive enough black hole. The crossing itself is geometrically smooth, but something has fundamentally and irreversibly changed. Inside the event horizon, the geometry of space-time has been altered in a way that has no parallel in ordinary experience. Every direction that previously pointed outward toward distant stars, toward safety, toward anything outside, has been bent by the curvature of space-time into a direction that points inward toward the center. Space and time have effectively exchanged roles. Moving toward the singularity at the center is no longer something that can be avoided by thrust or speed or clever navigation. It is as inevitable as the forward direction of time. you cannot choose not to move into the future. You cannot, from inside an event horizon, choose not to move toward the center. This is not a stronger gravitational pull than anything previously encountered. It is a change in the causal structure of space-time itself, a change in what directions are even possible. In 1965, the mathematician and physicist Roger Penrose proved this rigorously. Using a set of geometric techniques he developed specifically for the purpose, Penrose demonstrated that once an event horizon forms the formation of a singularity inside a point where space-time curvature becomes infinite and the equations of general relativity break down entirely, is mathematically inevitable. Not probable, not likely. Inevitable given the assumptions of Einstein's theory. This wasn't speculation. It was a theorem as logically binding as any proof in mathematics. If general relativity is correct, black holes don't just form, they must form. The singularity inside is not optional. Penrose received the Nobel Prize in Physics in the year 2020 for this work 55 years after he did it. Black holes are not accidents. They are not exotic edge cases. They are logical consequences of the way the universe is built, written into the mathematics of space-time itself, waiting to emerge whenever matter is compressed far enough. The universe doesn't have a mechanism to prevent them. It has, if anything, the opposite equations that guarantee them. If the event horizon has nothing physically special about it, and a person falling through wouldn't feel anything at the moment of crossing, why is it that information cannot escape? That is a question physics has not yet fully answered. But to understand why we need to look at something even stranger than black holes themselves, giants, weighing billions of times the mass of the sun that appeared when the universe hadn't had nearly enough time to create them. The James Webb Space Telescope was designed to see further back in time than any instrument before it. Further back means further away, because light takes time to travel. Looking deep into space is the same as looking deep into the past. Point Webb at a distant enough galaxy, and you're seeing that galaxy not as it is now, but as it was billions of years ago when the universe was young and still assembling itself. What Webb has been finding since it began returning data has quietly unsettled a significant portion of what astrophysicists thought they understood about the early universe. Among the most disorienting discoveries, supermassive black holes objects weighing millions of times the mass of the Sun already existed when the universe was only 420 million years old. Not 4 billion, not 2 billion, 420 million. That is less than 3% of the universe's current age of 13.8 billion years. One of these objects had already accumulated a mass of several million suns by that point. Others discovered in subsequent observations were similarly massive, similarly ancient, similarly impossible under the models that were standard just a few years ago. To understand why this is so disorienting, you need to understand a constraint called the Eddington limit. When a black hole pulls in surrounding gas and dust, that material doesn't fall straight in. It spirals inward, forming a flat, rotating structure called an accretion disk. Friction within the disk heats the gas to extreme temperatures, millions of degrees, causing it to radiate intensely across the electromagnetic spectrum. That outward radiation creates pressure. And if the black hole is feeding too aggressively, the radiation pressure becomes strong enough to push the infalling material back outward, effectively halting the accretion process. The Eddington limit is the theoretical maximum rate at which a black hole can accrete mass before its own radiation shuts the feeding down. It is not a soft guideline. It is a balance between two physical forces, gravity pulling inward, radiation pressure pushing outward, and it places a hard ceiling on how fast a black hole can grow at any given moment. Working backwards from that ceiling, astrophysicists can calculate how long it would take a black hole to grow from a stellar remnant, say a few tens of solar masses, to several million solar masses, assuming it feeds continuously at the Eddington limit the entire time. The answer is hundreds of millions to billions of years. Even under the most optimistic assumptions, the math doesn't produce a million solar mass black hole in 420 million years from a stellar mass starting point. And yet there they are, confirmed by multiple independent observations verified across different instruments, repeated in dataset after dataset. This is not a measurement error. This is data forcing astrophysics to reconsider its assumptions from the ground up. Three broad pathways have been proposed to explain how supermassive black holes could have grown so large so quickly. Each has genuine scientific support. None of them is fully sufficient on its own. The first is called direct collapse. In the early universe, before the first stars had formed and begun enriching the surrounding gas with heavier elements, conditions may have existed where a truly enormous cloud of pristine hydrogen and helium containing perhaps tens of millions of solar masses could have collapsed directly into a black hole without ever fragmenting into individual stars first. Under normal circumstances, as a gas cloud contracts, it cools by radiating energy and fragments into smaller clumps, each of which forms a star. But under specific early universe conditions, particularly in the presence of intense radiation from nearby sources that suppressed the cooling, the fragmentation might not have occurred. The entire cloud collapses as a single object, producing a seed black hole of 10,000 to 100,000 solar masses in one step, bypassing the stellar evolution pathway entirely. These would be called direct collapse black holes. The conditions required are quite specific, and no direct collapse black hole has yet been confirmed observationally, but the theoretical framework is solid and the search is ongoing. The second pathway is hierarchical merging. In the dense, chaotic environments of early galaxies, stellar mass black holes form in large numbers. Over time, dynamical friction, a gravitational drag effect, where a massive object moving through a field of lighter objects gradually loses momentum, causes these black holes to sink toward the galactic center. Once concentrated there, they merge repeatedly, building progressively more massive objects. The problem is timescale. This process is slow. The sinking and merging happen on timescales that, under conditions resembling even the densest early galaxies we can model, struggle to produce millions of solar masses within 420 million years. It works in principle. It simply doesn't work fast enough to explain what Webb is seeing. The third pathway is the most conceptually radical primordial black holes. These would be black holes that formed not from the collapse of stars or gas clouds, but directly from density fluctuations in the very early universe, fractions of a second after the Big Bang, long before any star had ever formed. If regions of space in the early universe were sufficiently overdense, they could have collapsed gravitationally into black holes without passing through any stellar phase at all. No direct evidence for primordial black holes currently exists, but they have not been ruled out, and certain mass ranges remain observationally unconstrained. If they exist in the right mass range, they could provide the seed objects that later grew through accretion and merging into the supermassive black holes Webb is now detecting. The most likely reality, as the evidence currently stands, is some combination of these pathways and possibly a fourth pathway that hasn't been fully articulated yet. The universe rarely uses a single mechanism when it can use several simultaneously, but here is the implication that cuts deepest. If supermassive black holes were already in place when the universe was only 420 million years old, if they predate the fully formed galaxies we observe around them, then the traditional picture of galaxy formation needs 10 to be inverted. The assumption had been that galaxies form first. Gas collapses under gravity, stars form the collective mass, produces a deep gravitational well, and eventually a supermassive black hole grows at the center of what is already a functioning galaxy. Black hole as product of galaxy. But if the black hole was there first, or grew to supermassive scale while the surrounding galaxy was still assembling, then the relationship runs the other way. The black hole's gravitational influence shapes the distribution of gas and stars forming around it. The galaxy assembles in the gravitational landscape the black hole has already created. Black hole as architect of galaxy. That is a fundamentally different picture of how cosmic structure emerges. And the data Webb is accumulating month by month is pushing increasingly in that direction. The question is not yet settled. The answer is not yet known. New findings arrive regularly, each one adding detail, each one sharpening the constraints. The picture is still being developed, which is precisely what makes it interesting. If black holes came before galaxies, does that mean the Milky Way formed because of Sagittarius A, not the other way around times? But regardless of which pathway created them, once a supermassive black hole has established itself at the bound, the center of a galaxy, it begins doing something no one predicted, reshaping everything around it, including the very conditions that made Earth and life possible. There is a question worth sitting with for a moment before moving forward. Sagittarius A star, the supermassive black hole at the center of the Milky Way, is currently quiet. It isn't actively feeding. It isn't blazing with energy. By the standards of supermassive black holes across the universe, it is remarkably dormant, to a sleeping giant. 4 million solar masses of compressed space-time sitting in the dark at the galaxy's center, doing very little that we can observe. This is actually unusual. Many supermassive black holes we observe in other galaxies are actively accreting material, producing enormous amounts of radiation, driving powerful outflows. Sagittarius A star right now is not. And that quiet has lasted long enough that the Milky Way has settled into a relatively stable, relatively calm state. The kind of state that allowed a small rocky planet to form in a quiet outer spiral arm, remain geologically stable for 4.5 billion years, and eventually develop conditions suitable for life. That connection is not coincidental. To understand it, you need to understand what happens when a supermassive black hole is not quiet. When a supermassive black hole is actively feeding, when significant amounts of gas and dust are spiraling into its accretion disk, the disk heats to tens of millions of degrees. At those temperatures, the disk radiates with an intensity that can reach the equivalent of thousands of billions of suns combined. Not the black hole itself, which remains dark, but the churning disk of superheated material surrounding it, one of the most luminous phenomena in the observable universe. That energy doesn't just radiate harmlessly outward into empty space. It interacts with the gas distributed throughout the surrounding galaxy. It heats that gas. And gas that has been heated to tens of millions of degrees cannot do what cold gas does. It cannot contract under its own gravity, cannot cool and fragment and collapse into new stars. The process of star formation, which requires cold, dense gas falling inward under gravitational attraction, is effectively suppressed across large regions of the galaxy whenever the central black hole is actively feeding. This is the feedback mechanism. The black hole feeds, produces energy, heats the surrounding gas, reduces the rate at which new stars form, and eventually reduces the supply of cold gas available to fall into the black hole itself. Activity declines. The black hole quiets. Over millions of years, the gas cools again, star formation resumes, eventually more material works its way toward the galactic center, and the cycle begins again. An automatic thermostat, no programmer required, running continuously for billions of years. A supermassive black hole operates like a central air conditioning unit for its entire galaxy. When it switches on, everything gets too hot for anything useful to happen. When it switches off, things get noisy enough that it has to switch back on. 4 billion years later, Earth was born, which is basically what cosmologists mean by room temperature. The consequences of this mechanism for our own existence are more direct than they might first appear. Consider what the Milky Way would look like without it. In the absence of feedback from a central supermassive black hole, the galaxy's gas supply accumulated over billions of years, from mergers, inflows, and stellar recycling, would have been available to form stars at a much higher rate in 10. The early universe. Galaxies without this regulatory mechanism tend in simulations and in observations of certain galaxy types to convert their gas into stars very rapidly in their early history, essentially exhausting their star-forming material in a few billion years, rather than spreading it across 10 billion or more. A galaxy that burned through its gas too quickly would have produced a very different stellar population. A surge of massive, short-lived stars, each tens or hundreds of solar masses, would have formed and died in quick succession, each one detonating as a supernova, flooding the surrounding space with ionizing radiation and high-energy particles. The interstellar environment in such a galaxy would have been far more energetic, far more turbulent, far more hostile to the formation of stable planetary systems around smaller, longer-lived stars like the Sun. Small, quiet, rocky planets, the kind that remain geologically and climatically stable for billions of years, long enough for complex chemistry to develop, are products of stable, calm, stellar neighborhoods. Those neighborhoods require a galaxy that has been regulated, one that didn't burn too fast too early. The evidence for this regulation is written into the observable properties of galaxies themselves. Astronomers have found a remarkably tight correlation called the M-sigma relation between the mass of a galaxy's central supermassive black hole and the velocity dispersion of stars in the galaxy's central bulge. Velocity dispersion measures how fast stars in the bulge are moving relative to one another, which reflects the depth of the gravitational potential. Well, they're embedded in, which in turn reflects the total mass of the stellar system. The correlation holds across 4 orders of magnitude in black hole mass, from millions to tens of billions of solar masses, and it holds with a precision that surprised everyone who first measured it. More massive black holes live in galaxies where the central stars are moving faster. The black hole mass scales with the bulge properties, even though the black hole's direct gravitational influence extends only across the innermost few light years, while the bulge extends across thousands. The black hole knows its galaxy, and the galaxy knows its black hole, in the sense that they have been shaping each other's growth throughout their entire shared history, locked in a feedback relationship spanning billions of years. If Sagittarius A star is dormant right now, what will happen when it wakes up next time, and what does that mean for the solar system? But that thermostat doesn't only work through radiation. It has a far more powerful weapon, jets of matter fired at nearly the speed of light, punching straight out of the galaxy. In the galaxy Messier 87, about 55 million light-years from Earth, a black hole, 6.5 billion times the mass of the Sun, is doing something that has no real parallel anywhere in ordinary experience. From its poles perpendicular to the plane of its accretion disk, it is firing 2 continuous streams of plasma outward into space. These jets travel at 99% of the speed of light. They extend for 5,000 light-years in each direction before eventually dissipating into the surrounding intergalactic medium. They have been observed from Earth using radio telescopes since the 1970s, a thin, bright line cutting across the galaxy at a speed our instruments can track in real time, its apparent motion across the sky, measurable year by year. 5,000 light-years, at 99% of the speed of light. Continuous for what appears to have been billions of years. The energy source for these jets is not, as you might assume, the material falling into the black hole. The infalling material certainly contributes. The accretion disk is intensely energetic, and some of that energy goes into the jets. But the primary energy reservoir powering the jets of the most active supermassive black holes is something more fundamental, the rotational energy of the black hole itself. A spinning black hole doesn't just sit there rotating in empty space. It drags space-time around, with it a phenomenon called frame dragging, predicted by general relativity and confirmed by satellite measurements around Earth, where the effect is tiny but detectable. Around a spinning supermassive black hole, this effect is not subtle. Space-time in the immediate vicinity is being pulled in the direction of the black hole's rotation continuously at a rate that increases sharply as you approach the event horizon. Magnetic field lines threading through the accretion disk get caught in this rotating space-time and twisted into helical structures around the black hole's rotational axis. Those twisted field lines act like a mechanism that extracts rotational energy from the black hole and channels it outward, accelerating plasma along the axis, producing the jets. The black hole slows very slightly with each burst of energy transferred. The jets are in a precise physical sense the black hole spending its rotational energy. The jets of the most powerful active galactic nuclei carry enough energy to do something extraordinary, push gas entirely out of the host galaxy. Not just heat it, not just slow the rate at which it forms stars, actually expel it, drive it beyond the galaxy's gravitational boundary into the surrounding intergalactic space, removing it permanently from the galaxy's star-forming budget. This is feedback, operating at the largest physical scale we can observe. A single object at a galaxy's center reshaping the gas distribution of an entire galaxy, influencing the star formation rate across a structure hundreds of thousands of light-years across. Imaging the black hole at the center of Messier 87 directly required solving a problem that had seemed for decades essentially unsolvable. The event horizon of the Messier 87 black hole, despite being roughly 40 billion kilometers across, larger than our entire solar system, is 55 million light-years away. At that distance, it subtends an angle on the sky of about 20 microarcseconds. To resolve something that small requires a telescope with an effective diameter of roughly Earth itself. No single telescope that large can be built. But the resolution of a radio telescope depends not on the physical size of its dish, but on the separation between its component receivers, a technique called very long baseline interferometry. By linking 8 separate radio observatories spread across multiple continents, from Hawaii to Spain to the South Pole, the Event Horizon Telescope collaboration created a virtual instrument with an effective aperture equal to the diameter of Earth. The observing campaign in April of 2017 produced approximately 5 petabytes of data, 5 million gigabytes. No internet connection on Earth could transfer this volume in any reasonable time frame. The hard drives had to be physically shipped by airplane from each observatory to central processing facilities. The South Pole Station's data had to wait months for weather conditions to allow a flight out. The image released in April 2019 shows a bright asymmetric ring of glowing plasma surrounding a central dark region, the shadow of the event horizon itself. The ring is not uniform. The southern portion is noticeably brighter than the northern. This asymmetry is not an artifact. It is a direct consequence of the black hole's rotation and the relativistic Doppler effect. The side of the accretion disk rotating toward us is boosted in brightness by its motion. The side rotating away is dimmed. The image itself encodes information about the black hole's spin. The size of the shadow matched the predictions of general relativity to within a few percent, the most precise test of Einstein's theory ever conducted in the regime of strong gravity. 3 years later, in 2022, the Event Horizon Telescope released an image of Sagittarius A star, the black hole, 26,000 light-years away, at our own galaxy's center. This image was paradoxically harder to produce than the Messier 87 image, despite the target being roughly 2,000 times closer. The reason is scale. The Messier 87 black hole is so large that material in its accretion disk takes days to weeks to complete a single orbit. The disk changes slowly enough that the telescope can integrate signal over many hours without the target significantly shifting. Sagittarius A star, being far smaller, has an accretion disk where orbital timescales are measured in minutes. The disk was changing faster than the telescope could take a clean snapshot, like trying to photograph a dog running at full speed rather than a mountain standing still. The collaboration had to develop new computational techniques, essentially algorithms, that could reconstruct a stable image from data that was continuously shifting during the observation before a usable image could be produced. The image shows the shadow of the event horizon, but tells us nothing about what lies inside. Will there ever be a day when we can observe what happens beyond the event horizon? The short answer is no, at least not with light. But in 2015, humanity heard for the first time the sound of 2 black holes colliding from a distance of 1.3 billion light-years, and it lasted only 0.2 seconds. At 5:51 in the morning, On September 14, 2015, a detector in Livingston, Louisiana registered something. 7 milliseconds later, a second detector in Hanford, Washington registered the same thing. The two signals were nearly identical, offset by exactly the time it takes light to travel between the two sites. The signal itself lasted 0.2 seconds. It began as a low rumble at 35 Hz, below the threshold of human hearing, but within the frequency range the detectors were built to sense. Over those 0.2 seconds, the frequency climbed steadily to 150 Hz, the amplitude growing as it rose, and then it stopped, abruptly. As if something had simply ceased to exist. That shape, the rising chirp, the sudden cutoff, was not arbitrary. It was a signature. Two black holes, one weighing 36 times the mass of the Sun and the other 29 times, had been spiraling toward each other across more than 1 billion years. In their final moments, they were orbiting each other hundreds of times per second, each moving at a significant fraction of the speed of light, the space between them shrinking with every orbit. When they finally merged, 1.3 billion years ago, the energy released in that fraction of a second exceeded the combined light output of every star in the observable universe, every galaxy, every sun, everything but released entirely, as gravitational waves completely invisible to any optical or radio telescope that has ever existed. What LIGO detected was the faint ripple of that event arriving at Earth, stretched thin across 1.3 billion light-years of travel. To understand what gravitational waves actually are requires letting go of the analogy to other kinds of waves. Sound waves are pressure disturbances moving through matter. Electromagnetic waves, light, radio, X-rays, are oscillating electric and magnetic fields moving through space. Gravitational waves are neither. They are disturbances in the geometric structure of space-time itself. When a gravitational wave passes through a region of space, the distances between objects in that region change, not because the objects are moving through space, but because space itself is briefly stretching in one direction and compressing, in the perpendicular direction, alternating as the wave passes. The distortion LIGO measured from this first detection was a change in the length of its 4-kilometer arms of less than 1,000th the diameter of a single proton, not a proton. 1,000th of a proton's diameter across 4 kilometers. Achieving that sensitivity required solving engineering problems that had no precedent. The mirrors at the ends of LIGO's arms, each weighing 40 kilograms, are suspended from a multi-stage pendulum isolation system designed to filter out every mechanical vibration from the surrounding environment. Ocean waves breaking on coastlines thousands of kilometers away, trucks passing on distant highways, microseismic activity from weather systems. All of it had to be attenuated to below the signal level being sought. The laser light itself introduces quantum noise. The photons arriving at the mirror create tiny random pressure fluctuations that must be accounted for and partially compensated. LIGO is by any reasonable measure the most precise measuring instrument humanity has ever built. And within days of being switched on after a major upgrade, it detected a signal that confirmed a prediction Einstein had made a century earlier and himself doubted would ever be measurable. Gravitational waves are real. Space-time carries information. The universe can be observed not just through light, but through geometry itself. Since that first detection, LIGO and its European counterpart Virgo have catalogued dozens of black hole mergers. Each one adds to a growing census of black hole masses, spins, and merger rates across cosmic history. Each one tests general relativity in conditions no laboratory on Earth can replicate. And so far, every single one matches Einstein's predictions with extraordinary precision. But one event stands apart for what it revealed about the limits of our understanding of stellar evolution. In May 2019, the detectors registered a merger catalogued as GW190521. The two black holes involved had masses of 85 and 66 times the mass of the Sun, respectively. The merger produced a remnant black hole of 142 solar masses, the first confirmed intermediate mass black hole ever directly observed. The problem is that neither progenitor should exist. Stellar evolution theory predicts a gap in the mass distribution of black holes formed from direct stellar collapse. Stars in a certain mass range, roughly between 65 and 130 times the mass of the Sun, undergo a process called pair instability before they can collapse. Photons in the core spontaneously create electron-positron pairs, destabilizing the star and triggering an explosion that destroys the entire object, leaving no remnant behind. No black hole forms. The star simply disintegrates. This means, according to theory, that stellar collapse cannot directly produce black holes with masses between roughly 65 and 130 solar masses. Black holes below that range exist. Black holes above that range, if they can form at all, require a different mechanism. The gap in between should be empty. GW190521 placed two black holes squarely inside that forbidden zone. Both of them. The most likely explanation is that these were not first-generation black holes objects, formed directly from stellar collapse, but second-generation ones, black holes that were themselves products of earlier mergers, combining smaller black holes into objects large enough to fall inside the mass gap and then merging again to produce what LIGO detected. Hierarchical mergers building black holes that stellar evolution alone cannot create. If this interpretation is correct, it means black hole populations in the universe are more layered and complex than anyone expected, with multiple generations of mergers building progressively more massive objects across cosmic time. If LIGO detected gravitational waves from 1.3 billion light-years away, what will LISA, operating in space, be able to hear from the full 13.8 billion-year history of the universe? Gravitational waves show us black holes colliding, but they don't answer the question that has kept physics awake for 50 years. What happens to everything that has fallen inside, and where does that information go? In 1974, Stephen Hawking was 32 years old and had been living with ALS for a decade. He could no longer write. He processed mathematics entirely in his head, developing an unusual visual and geometric intuition that his colleagues found almost impossible to follow. And that year, working through a calculation he had expected to produce an unremarkable result, he found something that changed the conceptual foundations of theoretical physics. Black holes are not completely black. The argument begins with a feature of quantum mechanics that has no classical counterpart. Empty space, a perfect vacuum with no particles, no radiation, no fields of any kind, is not actually empty in quantum theory. Quantum fields permeate all of space, and they fluctuate. Pairs of virtual particles, a particle and its antiparticle, spontaneously appear and annihilate each other continuously throughout the vacuum, borrowing energy from the uncertainty principle for intervals too brief to directly observe, then returning it. These are not hypothetical constructs. Their effects are measurable. They contribute to the Lamb shift in hydrogen spectra and to the Casimir force between conducting plates held close together. Near the event horizon of a black hole, something can happen to these fluctuations that transforms them from virtual to real. A pair appears just outside the horizon. Ordinarily, they would annihilate each other almost immediately. But if one member of the pair falls across the event horizon before annihilation can occur, the other is stranded on the outside, and with its partner gone, it becomes a real particle, carrying real positive energy, propagating away from the black hole as genuine radiation. From the outside, this looks exactly as if the black hole has emitted a particle, and it has at a cost. The black hole loses a small amount of mass in the process. Over time, this slow hemorrhage of mass means black holes evaporate. They don't last forever. The temperature of this radiation is inversely proportional to the black hole's mass. A black hole 10 times the mass of the Sun has a temperature of about 6 nanokelvin, 6 billionths of a degree above absolute zero. A black hole 1 million times the mass of the Sun is cold to 10 to the power of -14. Kelvin colder than the coldest regions of deep space. These temperatures are so low that for any black hole that exists in the real universe today, the Hawking radiation is utterly undetectable. overwhelmed by the cosmic microwave background and every other source of thermal radiation in the universe. But the principle is solid. The mathematical framework is consistent with everything known about quantum field theory in curved spacetime. This is not a speculative proposal, it is a derived consequence, confirmed independently by multiple approaches of applying quantum mechanics carefully to the geometry near an event horizon. And that is where the trouble starts. Quantum mechanics is built on a principle called unitarity. The quantum state of a closed system evolves in a way that is mathematically reversible. Information is never genuinely destroyed. It can be scrambled into an arbitrarily complex and inaccessible form, spread across enormous numbers of particles encrypted in correlations that are practically impossible to decode. But it is always there in principle, encoded in the total quantum state of all the particles involved. If you knew the exact quantum state of all the combustion products from a burning book, every photon, every molecule of smoke, every ash particle, you could in principle reconstruct the original text. The information is preserved, even if retrieving it is beyond any practical ability. Unitarity is not a convenience or an approximation. It is a foundational requirement of quantum mechanics. Violating it would cause probabilities to stop adding up to 1. It would allow energy to be created from nothing. It would unravel causality. Every precision measurement in atomic and particle physics implicitly confirms it. Hawking's calculation showed that the radiation a black hole emits is purely thermal, characterized only by the black hole's temperature, carrying no information whatsoever about what fell in. A black hole that swallowed an encyclopedia and one that swallowed the same mass of featureless hydrogen gas would emit identical Hawking radiation. When the black hole finally evaporates completely, every piece of information about everything that ever fell through the event horizon is simply gone. This is not a scrambling of information. This is a destruction of it, and it directly violates unitarity. Two of the most successful and precisely tested theories in the history of physics, general relativity and quantum mechanics, were producing flatly contradictory answers to the same question. One of them had to be wrong or incomplete or both. The most promising resolution points towards something called the holographic principle. In the early 1970s, the physicist Jacob Bekenstein made a discovery that seemed at first like a strange coincidence. He found that the entropy of a black hole, the thermodynamic measure of its internal disorder, the count of its microscopic configurations, is proportional not to its volume, as entropy is for ordinary objects, but to the area of its event, horizon. Specifically, it equals 1/4 of the horizon area, measured in units of the Planck length squared, where the Planck length is approximately 10 to the power of -35 meters. This is a deeply unusual result. For any ordinary object, a gas, a liquid, a solid, entropy scales with the number of constituent particles, which scales with volume. For a black hole, entropy scales with the surface that bounds the volume. It is as if all the information about the interior is somehow encoded on the two-dimensional boundary, not distributed through the three-dimensional space inside. The holographic principle, developed through the work of Gerard Hooft-Leonard Susskind and later Juan Maldacena's anti-de Sitter space correspondence, formalizes this idea. All of the information contained within a volume of space can in principle be encoded on the two-dimensional boundary of that region, just as a hologram encodes three-dimensional information on a flat surface. Applied to black holes, this suggests that everything that falls in is not lost inside the three-dimensional interior, but is imprinted on the event horizon in a form that is then gradually re-emitted, scrambled but present in the Hawking radiation. In 2019 calculations, using what has been called the island formula, demonstrated that properly accounting for quantum entanglement between the black hole and the radiation it has already emitted yields a result consistent with information preservation, the so-called page curve, which describes how the entropy of the radiation should behave over the full lifetime of the evaporation if information is conserved. Hawking himself defended the view that information is destroyed for decades and conceded the point in 2004 though the precise physical mechanism by which information escapes remains to this day an open question. If the holographic principle is correct, and three-dimensional information can be fully encoded onto a two-dimensional surface, what does that tell us about the nature of the three-dimensional space we're living in, right? Now, the information paradox has not been fully resolved, but it has opened a question that goes even deeper. If black holes are genuine thermodynamic systems, with real temperature and real entropy, what are they telling us about the nature of space-time itself? Carl Schwarzschild found his solution in weeks, dying in a trench, but his solution described the simplest possible case. A black hole that isn't moving, isn't rotating, sitting alone in an otherwise empty universe. Clean, elegant, and almost certainly never found in nature. Because in the real universe, everything spins. The gas clouds that collapse into stars are rotating. The stars themselves rotate. When they die and their cores collapse, angular momentum, the physical quantity that describes rotation, is conserved. A collapsing core that was rotating slowly, as a star will spin dramatically faster as a compact remnant. The same way a figure skater pulling in their arms accelerates their spin. The black holes that form from stellar collapse are born spinning. The supermassive black holes at galactic centers have spent billions of years accreting, rotating gas, and merging with other spinning objects. Almost every black hole we have reason to believe exists in the real universe is rotating, some of them near the theoretical maximum. Solving Einstein's field equations for a rotating mass is enormously harder than solving them for a stationary one. It took 48 years after Schwarzschild's work before anyone managed it. In 1963, Roy Kerr, a New Zealand mathematician working at the University of Texas, found the exact solution for a rotating black hole. The Kerr solution, as it is now called, describes a geometry far stranger than anything Schwarzschild's work had hinted at. A rotating black hole is not spherical. It bulges at its equator, compressed at its poles, shaped by the centrifugal effects of its own spin. And it does something that a non-rotating black hole cannot. It physically drags space-time around with it in the direction of its rotation. This effect, called frame dragging, is a genuine prediction of general relativity, not an artifact or approximation. Any rotating mass drags space-time to some extent. Earth does it, the Sun does it. The effect around ordinary objects is minuscule, so minuscule that measuring it around Earth required a satellite called Gravity Probe B, which spent 5 years in orbit collecting data before the result was confirmed in 2010. 11. The measured frame dragging from Earth's rotation matched general relativity's prediction to within a fraction of a percent. Around a rapidly spinning black hole, the effect is not minuscule, it is overwhelming. Space-time near the black hole is being dragged around like water circling a drain, not metaphorically, but in a precise mathematical sense. Nothing in that region can remain stationary with respect to distant stars, regardless of how much thrust it applies. The geometry itself is in motion. This leads to one of the most remarkable features in all of general relativity, the ergosphere. Outside the event horizon of a rotating black hole lies a region called the ergosphere, a zone bounded on the inside by the event horizon and on the outside by a surface called the static limit. The shape of this region is not spherical. It bulges at the equator and touches the event horizon at the poles, forming an oblate shell around the spinning black hole. The ergosphere is unlike the event horizon. In one crucial respect, it can be entered and exited. Crossing the static limit inward does not commit you to the black hole's interior the way crossing the event horizon does. You can enter the ergosphere and with sufficient energy expenditure, escape back out. You are not trapped. But inside the ergosphere, you cannot stand still. The frame dragging is so severe that everything matter, light, any physical object is forced to rotate in the direction of the black hole's spin. You can move faster or slower in the rotational direction, but you cannot move opposite to it fast enough to appear stationary to a distant observer. The geometry has made stillness physically impossible in this region. This constraint is not merely inconvenient, In 1969, Roger Penrose recognized that it creates something extraordinary, a mechanism for extracting energy from the black hole itself. Here is how it works. An object enters the ergosphere on a carefully chosen trajectory and splits into two pieces, perhaps a spacecraft jettisoning cargo or a particle undergoing decay. One piece is directed onto an orbit with negative energy as measured by a distant observer. This is possible only inside the ergosphere, where the frame dragging creates the conditions for negative energy trajectories to exist. That piece falls into the event horizon, carrying its negative energy into the black hole. The other piece escapes the ergosphere, and when its energy is measured by a distant observer, it has more energy than the original object that entered. Where did the extra energy come from? The black hole. The infalling negative energy piece reduced the black hole's total energy, which means it reduced its mass, and specifically its rotational energy. The black hole slows down very slightly, and that rotational energy has been transferred to the escaping piece. The theoretical maximum energy extractable through this process from a maximally rotating black hole is 29% of the black hole's total mass energy. Compare that to nuclear fission, which converts less than 1% of mass to energy, or nuclear fusion, which reaches perhaps a fraction of a percent under the best conditions. A rotating black hole is by a wide margin the most energy-dense reservoir that physics permits. Essentially, a spinning black hole is a cosmic battery charged by infalling matter discharged through its jets. Nature invented the rechargeable battery before humanity knew what fire was. This isn't purely theoretical. Nature appears to be running the Penrose process or something closely related to it right now in galaxies across the observable universe. The mechanism that most closely matches observations is called the Blandford-Znajek process, proposed in 1977. Magnetic field lines thread through the accretion disk and into the ergosphere. As space-time rotates, it winds these field lines into helical structures around the black hole's rotational axis. The twisted field lines act as a conduit channeling rotational energy from the ergosphere outward and accelerating plasma along the axis. The result is a jet. Magnetohydrodynamic simulations and the Event Horizon Telescope observations of Messier 87 are consistent with this mechanism operating in that system. The jet, extending 5,000 light-years from the Messier 87 black hole, traveling at 99% of the speed of light, has been powered for billions of years by the rotational energy of the black hole at its center. One object at the heart of a galaxy, continuously powering a structure thousands of times larger than the entire solar system for longer than Earth has existed. That is what a spinning black hole actually is, not just a gravitational well, but an engine. A reservoir of rotational energy stored in the geometry of space-time, accessible through the physics of the ergosphere, spent gradually over billions of years in the most energetic continuous outflows the universe produces. If a spinning black hole is a theoretically exploitable energy reservoir, what prevents physics from developing a practical extraction method, and what technological threshold would be required? That energy reservoir does not last forever, and the way a black hole ends its existence reveals the deepest truth about what role these objects play in the universe. There is a number worth sitting with before continuing: 10 to the power of 67. That is the approximate time in years for a black hole with the mass of the Sun to evaporate completely through Hawking radiation. Not 10 billion years, not a trillion years, 10 followed by 67 zeros. To develop any intuition for this number, consider the following comparison. The universe is currently about 13.8 billion years old, roughly 10 to the power of 10 years. The ratio between 10 to the 67 and 10 to the 10 is 10 to the 57. If the entire current age of the universe were compressed into a single second, the evaporation time of a solar mass black hole would be approximately 3 times 10 to the 49 years. You would need to run that compression again, the entire age of the universe, into 1 second, and repeat it for an incomprehensible number of iterations before the time elapsed would approach the evaporation timescale. For a supermassive black hole, 1 billion times the mass of the Sun, the evaporation time is 10 to the 98 years. This number has more digits than there are atoms in the observable universe. It is for any practical purpose beyond the reach of analogy. These are not just large numbers. They are a statement about what black holes actually are in the long arc of cosmic time, the most persistent structures the universe is capable of producing. To understand what the universe looks like when black holes finally evaporate, it helps to walk forward through the timeline of cosmic history. At roughly 10 to the 14 years from now, the last stars will exhaust their nuclear fuel and go dark. The smallest red dwarfs, which burn hydrogen at the most miserly possible rate, will be the final ones to fade. After that, the universe will contain no new sources of starlight. The night sky, from any hypothetical vantage point, will be permanently dark. At roughly 10 to the 19 years, gravitational dynamics will have gradually dismantled most planetary systems. Over timescales, this long gravitational interactions between stars passing near each other will randomize orbital energies. Planets will be slowly scattered outward into interstellar space or nudged inward to spiral into their cooling stellar remnants. The ordered architecture of solar systems will dissolve. At roughly 10 to the 37 years, white dwarfs, the cooling remnants of sun-like stars, will have radiated away the last of their thermal energy. Their cores, composed largely of carbon and oxygen, will crystallize into something resembling a diamond the size of Earth. These black dwarf stars will be cold, dark, and inert, emitting no detectable radiation, drifting silently through an expanding universe. From around 10 to the 40 years onward, black holes are the only objects with significant internal structure remaining anywhere in the universe. Everything else has either dispersed, cooled to the background temperature, or been incorporated into black holes through gradual gravitational capture. The universe at this stage is extraordinarily sparse, individual black holes, separated by distances that make the current distances between galaxies seem intimate, occasionally crossing paths over timescales of trillions of years, sometimes merging when they do, but mostly drifting in, isolation slowly, imperceptibly shrinking. And slowly is the operative word. For most of a black hole's life, the evaporation is so glacially slow as to be effectively unmeasurable. A solar mass black hole radiates at a power output of roughly 10 to the power of -28 watts. A single photon from a distant star carries more energy than a solar mass black hole radiates in years. The universe's background radiation, the cosmic microwave background, is currently far hotter than the Hawking temperature of any black hole that exists. Black holes, for most of cosmic history, are actually absorbing more energy from their environment than they are radiating away. True net evaporation won't begin for most black holes until the universe has cooled sufficiently that the background temperature drops below their Hawking temperature, which won't happen for an enormous span of time yet to come. But the end, when it finally comes, is not quiet. As a black hole loses mass, its temperature rises, because Hawking temperature is inversely proportional to mass. As the temperature rises, it radiates faster. As it radiates faster, it loses mass faster, which raises the temperature further. This is a runaway feedback loop, accelerating without limit as the black hole approaches zero mass. For almost the entirety of its 10 to the 67-year lifespan, a solar mass black hole changes imperceptibly. And then, in its very last second, after all that geological eternity of near stillness, it undergoes a violent final burst. The temperature reaches billions of degrees. The energy released in that final second is equivalent to millions of nuclear weapons detonating simultaneously. A brief, intense flash of radiation and particles, gamma rays, electrons, positrons, everything the temperature can thermally produce, expands outward into space. And then there is nothing. No event horizon, no space-time curvature, no structure of any kind. Just an expanding sphere of thermal radiation, indistinguishable from the background of a cold, dark, nearly empty universe, carrying within it, encoded in quantum correlations of extraordinary complexity, the information about everything that ever fell in. If unitarity holds, if the holographic principle is correct, if the information paradox resolves the way the most recent calculations suggest it does, the black hole that spent 10 to the 67 years as the most enduring structure in existence ends in a flash lasting less than a heartbeat, leaving behind nothing but light. After the last black hole evaporates in a universe that contains nothing but thin thermal radiation, is there anything that could happen next, or is that truly the end? The answer to that question is not just physics, it is the key to understanding why black holes are not a cosmic accident, but an irreplaceable part of the logical structure of reality itself. We have traveled a long way through this story. From a star running out of iron, to a dying physicist solving equations by candlelight in a trench, to the first photograph of a shadow cast by curved space-time, to a signal lasting 0.2 seconds that confirmed a century-old prediction, to the thermodynamic properties of objects that won't finish evaporating for 10 to the 98 years. Now it's time to answer the question we started with. Why does the universe need black holes? The honest answer is that it isn't a single answer. It's 6 answers, arriving from 6 completely different directions in physics, and all 6 are simultaneously correct. Start with mathematics. General relativity has been tested more thoroughly than almost any theory in the history of science. GPS satellites require relativistic corrections to keep accurate time without them. Positioning errors would accumulate at roughly 11 kilometers per day. The precession of Mercury's orbit, unexplained for decades under Newtonian gravity, is accounted for precisely by Einstein's equations. Gravitational lensing of light around massive objects measured to extraordinary accuracy in countless observations matches general relativity's predictions without deviation. Gravitational waves detected dozens of times now across a growing range of masses and distances match the theoretical waveforms calculated from Einstein's field equations with a precision that leaves essentially no room for alternative explanations. Every test we have run on general relativity across more than a century and across an enormous range of conditions has confirmed it. And general relativity applied consistently to matter dense enough produces black holes as a mathematical inevitability, not a possibility, not a likely outcome. An inevitability proven by Penrose's theorem, once an event horizon forms a singularity inside, is guaranteed by the internal logic of the theory itself. To deny black holes is to deny Einstein. To deny Einstein is to deny GPS, to deny the confirmed waveforms of gravitational wave detections, to deny the observed bending of light around galaxy clusters. The mathematics does not offer an exit. Move to astrophysics. The Tolman-Oppenheimer-Volkoff limit defines the maximum mass a neutron star can have before neutron degeneracy pressure is overwhelmed by gravity. The exact value depends on the equation of state of nuclear matter, which we don't fully understand, but it lies somewhere between roughly 2 and 3 times the mass of the Sunday. Above that threshold, no known force in the standard model of particle physics, no exotic interaction proposed by any currently viable theoretical extension, provides sufficient resistance to halt the collapse. When a stellar remnant exceeds this limit, collapse continues. It does not pause at some intermediate stable state. It does not find a new equilibrium. Space-time curves past the point where any outward direction remains geometrically available and a black hole forms. This is not a failure of nature. It is nature operating exactly as its laws dictate, without exception and without negotiation. Matter that is dense enough becomes a black hole. That is what the physics says. And the universe routinely produces matter dense enough. Consider galactic evolution. We explored this in detail, but the conclusion bears restating from this angle. A universe without supermassive black holes at galactic centers is a universe without the feedback mechanism that regulates star formation across cosmic time. Without that regulation, galaxies convert their gas into stars too rapidly in their early history, producing an early universe crowded with massive short-lived stars that detonate in rapid succession and flood their neighborhoods with ionizing radiation and high-energy particles. In that universe, the conditions required for stable, long-lived planetary systems around quiet, sun-like stars, conditions that depend on a galaxy that has been thermally regulated for billions of years, become vastly less likely to arise. The M-sigma relation, which holds across 4 orders of magnitude in black hole mass and which reflects billions of years of coevolution between black holes and their host galaxies, is not a coincidence. It is the signature of a universe in which supermassive black holes are structural components of galaxies, not incidental residents. A universe without them is a fundamentally different universe, almost certainly a more violent and less structured one, and very likely one less hospitable to the kind of complexity that eventually produces observers asking questions about it. Now, thermodynamics. When a massive star collapses into a black hole, entropy increases dramatically. A stellar mass black hole has enormously more entropy than the star that formed it. The entropy of a black hole scales with the area of its event horizon, and the numbers involved dwarf anything associated with ordinary stellar matter. Black hole formation is, from a thermodynamic standpoint, a highly favorable process to the universe moving toward higher entropy configurations, as the second law demands it always do. This means black holes are not just permitted by thermodynamics, they are thermodynamically preferred. Given sufficient concentration of mass, a black hole represents the highest entropy state available, and the universe's tendency toward entropy increase makes the formation of that state not just possible, but natural, in exactly the same sense that heat flows from hot to cold, and gases expand to fill available volume. Black holes exist partly because the universe is always seeking higher entropy, and black holes are where entropy goes to reach its maximum for a given concentration of mass. Then, quantum theory. Black holes are the only places in the observable universe where general relativity and quantum mechanics are both simultaneously inescapably relevant, where neither theory can be ignored and neither can be applied without the other. The Hawking radiation that slowly evaporates black holes is a quantum effect in curved spacetime. The information paradox arises because quantum unitarity and relativistic event horizons make incompatible predictions. The holographic principle, which emerged from trying to understand black hole entropy, may be the most important conceptual development in theoretical physics in the last 50 years, with implications for our understanding of spacetime that extend far beyond black holes themselves. Black holes are natural laboratories that the universe has constructed for probing the intersection of its 2 deepest theoretical frameworks. Without them, the contradictions between general relativity and quantum mechanics might remain hidden indefinitely, buried in regimes too extreme to observe. With them, those contradictions become impossible to ignore, and resolving them forces the development of whatever deeper theory eventually unifies gravity and quantum mechanics. Black holes don't just exist within physics, they are pushing physics forward. Finally, cosmology. On the longest timescales, the 10 to the 67 years, and beyond that we traced in the previous part, black holes are not permanent fixtures of the universe. They form during certain epochs, dominate during others, and eventually evaporate. They are phases in the evolution of matter and energy, not eternal monuments. Their existence is appropriate to a particular range of conditions in the universe's history, and they will eventually give way to a state of maximum entropy in which they no longer exist. This is precisely what makes them necessary. They are the universe's way of processing matter through a specific stage of its thermodynamic journey, concentrating mass, maximizing local entropy, regulating galactic structure, and ultimately dissolving back into radiation. They are steps in a process, not obstacles to it. And here is the thing that ties all 6 answers together. Black holes exist not despite the laws of physics, but because the laws of physics are applied consistently all the way to the end without exception, without a special case carved out for extreme conditions, without a point at which the black universe decides that the rules no longer apply. That is the real answer. The universe has one set of rules. Those rules produce black holes when applied without compromise, to matter dense enough, massive enough, concentrated enough. There is no version of a universe with the same laws that doesn't also have black holes. They are written into the logical structure of how things work at the deepest level we have so far understood. The true miracle is not that black holes are extreme, it is that the universe is consistent. Right now, 26,000 light-years from where you are sitting, Sagittarius, a star is lying still in total darkness. It doesn't glow, it sends no signal. But 4 million times the mass of the Sun is bending space-time with enough force to hold 200 to 400 billion stars in orbit around it. And we creatures living on a small rocky planet orbiting one of those stars have used mathematics, light and gravitational waves to understand that. Black holes are not the miracle in this story. The miracle is that we understand them, knowing that the existence of Earth and life may depend on the feedback loop of a black hole 26,000 light-years away. What does that change about how you think of your place in the universe?